In this video, we'll explore a few different measures of uncertainty. In thinking about uncertain events, some classic examples might come to mind, such as the outcome of a coin flip or the outcome of a six-sided dice roll. But uncertainty really rules everything. For example, in thinking about just human behavior, we might be interested in the uncertainty around whether or not a person votes or how they vote. And please don't be distracted by the fancy picture here. Or we might be interested in the uncertainty around whether or not a mountain climber successfully summits their peak. For any uncertain event, we can ask, what are the chances? We'll consider three different approaches to answering this question, or measuring uncertainty: probability, odds, and log odds. Let's start with perhaps the most familiar, the probability of an event. We'll denote probability by p. And in working with probability, there are really just a few fundamental properties that we need to understand. First, probabilities can range from 0 to 1. At these extremes, an impossible event has a probability of 0, and a certain event has a probability of 1. Halfway between these two extremes, an event that is equally likely to happen or not happen, that is a 50-50 event, has a probability of 0.5. Thus, 0.5 really marks a tipping point on the probability scale, marking a division between events that are less likely to happen and those that are more likely to happen. Consider some examples. The probability that your friend can fly is presumably 0, and the probability that the sun will rise tomorrow is 1. In the middle, if we flip a fair coin, there's a 50-50 chance we see heads. Instead, if we roll a six-sided dice, there's a 4 out of 6 or 2/3 chance that we get one of the 4 sides labeled 1, 2, 3, or 4, and a 2 out of 6 or 1/3 chance that we get one of the 2 sides labeled 5 or 6. Consider a second way to communicate the same information: odds. Odds are calculated by the ratio of p, the probability that an event happens, versus 1 minus p, the probability that an event doesn't happen. Thus, odds, notice, are a function of probability, plotted here. Notice both mathematically and in our picture, when probability p is 0, that is, an event is impossible, the odds of the event are also 0. For 50-50 events, with probability 0.5, the odds are 1. And the more and more certain an event, or the closer its probability is to 1, the greater and greater the odds. Mainly, as probability approaches 1, the odds grow without limit. Thus, unlike probability, which measures uncertainty on a 0 to 1 scale, the corresponding odds of an event can range from 0 to infinity. And the tipping point on the odds scale is 1, corresponding to 50-50 events that are equally likely to happen or not happen. Thus, odds below 1 indicate an event is less likely, and odds above 1 indicate an event that's more likely than not. Let's consider how probability and odds can both be used to measure the uncertainty of an event. Suppose there's a 0.95 probability of snow tomorrow, or a 95% chance. To translate this information into odds, we compare the probability that it snows, p, to the probability it doesn't snow, 1 minus p. That is, we compare a 95% chance of snow to the 5% chance of no snow. The result is an odds of snow equal to 19, or some people say 19 to 1 odds. Considering that this figure was calculated by the probability ratio below, we can interpret this to mean that it's 19 times more likely to snow than to not snow tomorrow. Next, we saw earlier that there's a 4/6 probability of seeing a 1, 2, 3, or 4 in a roll of a fair six-sided dice. To translate this uncertainty to the odds scale, we compare this probability of getting a 1, 2, 3, or 4 to the probability that we don't see this outcome, or equivalently, that we see a 5 or 6. A little math and rearranging shows that the ratio of these two probabilities, 4/6 to 2/6, is 2, or 2 to 1. Thus, we're twice as likely to get a 1, 2, 3, or 4 on a dice roll than to not, that is, than to get a 5 or 6. Similarly, consider the 50-50 event of observing heads in a fair coin flip. In this case, the probability of getting heads is equal to the probability of not getting heads, that is, the probability of getting tails. Both probabilities are 0.5. Thus, the odds of this event are 1. Oops, sorry about that. We're equally likely to get heads or tails. So whenever we see an odds of 1, it again indicates a 50-50 event. Recall that a 0.5 probability, and equivalently an odds of 1, is the tipping point between events that are more likely and events that are less likely. Thus, we could show that the event of seeing a 5 or 6 on a dice roll has a probability of 2/6 and a corresponding odds of 1/2, or 1 to 2 odds. Again, since these odds are a comparison of how likely an event is to happen versus not happen, 1 to 2 odds indicate that we're half as likely to get a 5 or 6 on our dice roll than a 1, 2, 3, or 4. Also notice that 1/2 is simply the inversion of 2, the odds for the opposite event, that of getting a 1, 2, 3, or 4. Finally, if there's a 0.05 probability or 5% chance that tomorrow is above freezing, the corresponding odds can be calculated at 1/19th, or 1 to 19 odds. In other words, with odds so close to 0, this event is unlikely. More specifically, the chances that it's above freezing are 1/19th of the chances that it's below freezing. Or again, if we invert this, 1/19th to 19, or 0.05 to 0.95, it's 19 times more likely to be below freezing than above. Consider a third and final way to communicate uncertainty: log odds. By default in statistics and RStudio, log refers to natural log ln with base e. For our purposes, we won't be needing to do a lot of mathematical manipulations of logs, but we do need to understand a few key log properties. First, to convert a log odds calculation back to a more meaningful odds scale, we can take e to the log odds, as written here. Mainly, e and log cancel each other out. Next, recall that probabilities range from 0 to 1, and odds range from 0 to infinity. The log function of odds is shown here. Notice that the more and more uncertain an event, or the closer its odds are to 0, the log odds of the event decrease without limit. Similarly, the more and more certain an event, or the greater its odds, the log odds increase without limit. Further, notice that the log odds cross 0 at the tipping point for 50-50 events with an odds of 1. Thus, unlike probability, which measures uncertainty on a 0 to 1 scale, and odds, which measure uncertainty on a 0 to infinity scale, the corresponding log odds can range from negative infinity to infinity, and the tipping point on the log odds scale is 0. Thus, negative log odds indicate an event that is less likely, and positive log odds indicate an event that is more likely. Thus, for each of our earlier examples, we can measure uncertainty on the probability, odds, and log odds scales. It's important to recognize again that these are just 3 different ways to say the same thing, and they're on different scales. Importantly, notice, highlighted in red, notice our tipping point of a 50-50 event with an odds of 1 and a log odds of 0. Events that have greater than 50-50 probability have positive log odds. Those that have less than 50-50 probability have negative log odds. Now, in our work, we'll often be translating between these three scales. For example, suppose the probability P of observing heads on a coin flip is 0.5. Then the odds of observing heads are calculated by P divided by 1 minus P. Hence, in this case, are 1. And finally, the log odds of observing heads are calculated by the log of our odds, or the log of 1, the result being 0. But more often than not, we'll want to translate uncertainty in the opposite direction. We'll start with an uncertainty on the log odds scale. And then, since log odds are difficult to interpret, we can translate this uncertainty to the odds scale by exponentiating. So taking e to the log odds. Finally, a little algebra shows that just as we can translate probability into odds, we can translate odds back into probability by dividing odds by odds plus 1. Consider an example. Suppose that the log odds of an event are negative 2.3. The negative sign here indicates that this event has less than a 50-50 chance of happening, but it's otherwise difficult to interpret the magnitude of its uncertainty. Exponentiating, using the exp function in R, indicates that the odds corresponding to this event are roughly 0.1, or only 1 in 10. Finally, converting to the probabilities scale, this event has a roughly 9% chance of happening. Now, I've made this calculation in two ways. Taking my odds, here, 0.100, etc., divided by that same number plus 1. And in the second approach, I'm just being more cautious about the potential impact of rounding and plugging in e to the negative 2.3 for my odds directly.